Another test that may be performed when making inferences about a single population is the t-test about a population mean. Similar to the z-test for the population mean, we use this particular test if we are making an inference about an average of a population. So the variable we are dealing with is quantitative. Next, since this is based on the t-distribution, which is normally distributed, this requires that the sampling distribution of the sample mean is normally distributed. However, what makes this different from the z-test for the population mean is that this does not require a value for the population standard. The t-test for the population mean is the test that is appropriate in cases wherein the population standard deviation is unknown, which is more usual. So this is a more common experience because in most cases, aside from the population mean, we also don't know the population standard depth. And therefore, a more appropriate test would be a t-test for the population mean. Now, the t-test about the population mean also differs from the z-test in terms of the formula for the test statistic. So first, instead of a z-test statistic, we will now compute for a t-test statistic. But the overall formula is still very similar to the z-test statistic. So the numerator is still the sample mean minus the constant in the null and the alternative hypotheses. But now for the denominator, since the population standard deviation is unknown, we will estimate it using the sample standard deviation. So instead of sigma, we will use S when computing for the test statistic. And this t distribution is based on n minus 1 degrees of freedom. This slide shows the differences in the rejection rule depending on the alternative hypothesis for the case that we are making inferences for. So for examples involving a one-sided greater than alternative, the rejection rule is to reject the null hypothesis if the test statistic exceeds the critical value. Or in other words, the rejection area is the area to the right of the critical value. And if the test statistic is inside that rejection area, then we reject the null hypothesis. For one-sided less than alternative, the rejection rule is the area to the left of the test statistic, or is the area to the left of the critical value, and the critical value is a negative critical value. It's the z-score with an area of alpha to its left. So if the test statistic is lower than that negative critical value, then we can reject the null hypothesis. Now, for two-sided not equal to alternative, the rejection rule states that if the test statistic is either less than or greater than the positive or the negative critical value, then we will reject the null hypothesis. So again, this is two-sided. So you have two critical values, one that is positive and one that is negative. If the test statistic is either less than the negative critical value or greater than the positive critical value, or in other words, if the test statistic is inside any of the two rejection areas, then we can reject the null hypothesis. For the p-value method, for the three types of alternatives, the rejection rule is the same. If the p-value is less than alpha, then we can reject the null hypothesis. But again, what differs is how to get the p-value. So again, for one-sided greater than, the p-value is the area to the right of the test statistic. For one-sided less than alternative, the p-value is the area to the left of the test statistic. Meanwhile, for two-sided not equal to, the p-value is either area to the left of the negative test statistic times 2, or area to the right of the positive test statistics times 2, or to consider both, to encapsulate both, just get the absolute value. So always look at the positive test statistic, get the area to its right, and then multiply that by 2. So that will be the p-value for two-sided not equal to. And if that p-value is less than alpha, then for that value of alpha, we can reject the null hypothesis. So let's consider this example for this particular test. In 1991, the average interest rate charged by the US credit issuers was 18.8%. Since then, new credit cards affiliated with retail stores, oil companies, etc., proliferated. A financial officer wishes to study whether the increased competition in the credit card business has reduced interest rates. From a sample of 15 interest rates, the mean was calculated to be 16.827% with a standard deviation of 1.5838%. Assume that the population of interest rates is normally distributed. So in this particular example, our objective is to determine if the increased competition has reduced the average interest rate. And based on that, we can formulate the null and the alternative hypothesis. So the null hypothesis will be that the mean is greater than or equal to 18.8%. And the alternative hypothesis states that the mean is less than 18.8%. So that's what you want to know. Is the average now less than what is currently known, which is 18.8%? So in this example, we will also use the same four values of alpha, 10, 5, 1, and 0.1%. And then we will confirm that the appropriate test is now the t-test for the population mean. So first, we are making an inference about an average interest rate, which is a population mean. Next, the sampling distribution is exactly normal. Our sample size is 15, but that is okay because the problem tells us that the individual interest rates are normally distributed. So since the distribution itself of the variable is normal, then there is no need for the central limit theorem. The sampling distribution is already exactly normal. Finally, like in most situations, we don't know the population standard deviation. What is given is 1.5838%, which is a standard deviation from the sample of 15. So since sigma is unknown, the appropriate test now would be the t-test for the population mean and not the z-test. So in this particular example, we will look for critical values using the critical value method. Remember, this is one-sided less than. So our critical value should be negative. Now, how were these critical values obtained? Again, this is the critical value because this is the t-score with an area of 10% to its left. So how was negative 1.345 obtained? So remember, the sample size here in this problem is 15, which means that the degrees of freedom is 14. So when looking for the critical value in the t-table, we look at degrees of freedom 14. So in this example, our table by default gives us positive t-scores, but since the t-distribution is normally distributed and is symmetrical with respect to the mean, then we can just get the mirror image of that to get the negative critical values. So instead of looking for the t-score with 10% to its left, we will look for the t-score with 10% to its right here in this table, and then just convert that to negative later. So again, for an alpha of 10%, we will look for this particular t-score with the appropriate degrees of freedom. So df again is 14, and under t sub 0.1, we have 0.1345, which means that 1.345 has an area of 10% to its right. And therefore, the mirror image of that, negative 1.345, will have 10% to its left. That's why the critical value for an alpha of 10% is negative 1.345. So the rest of the other critical values were obtained using the same procedure. So for 5%, the critical value should be negative 1.761. For 1%, the critical value is negative 2.624. And finally, the critical value for an alpha of 0.001 is negative 3.787. So those were the critical values obtained from the t table. And now we will compute for the test statistic, which will be compared to these critical values. So our test statistic is computed using this formula. Again, that's the sample mean minus the constant in the hypothesis divided by the sample standard deviation over the square root of the sample size. So all of these information were given here in the problem: sample mean, sample standard dev, and the sample size. So computing for the test statistic gives us negative 4.825, which is less than all of these critical values. So in other words, the test statistic is inside all the four rejection areas for all these four values of alpha. Therefore, for all these four values of alpha, our decision will be to reject the null hypothesis. And in terms of the weight of evidence, at an alpha of 0.001, we have extremely strong evidence. So there is extremely strong evidence that supports the hypothesis that the increased competition in the credit card business has reduced interest rates to less than 18.8%. Or in other words, there is extremely strong evidence to support the alternative hypothesis that the average interest rate is now less than 18.8%. Okay, so that's using critical value method. Now for p-value method, what will change is how we look for the p-value. So now the p-value is based on the test statistic, which is theoretically the area to the left of this test statistic. Again, unfortunately, our t-table only gives us areas to the right, okay, or positive t-scores. So again, we will use the symmetrical t-table in order to look for the p-value for this example. So again, we are looking for negative 4.825 somewhere here, which should have the same area as the the positive test statistic. So positive 4.825, the area to its right, should be the same as the area to the left of negative 4.825. And therefore, using this table, we will look for the area to the right of positive 4.825. So in degrees of freedom 14, we will look for that t-score 4.825. But as we can see here, it's not in this row. If you look at the trend, it keeps on increasing. As the t-score increases, the area to the right decreases. And the t-score we're actually looking for is even beyond this. So we can expect that the p-value, or the area to the right of 4.825, will be even lower than this one. So we won't be able to get the exact p-value, but our estimate is that it should be less than the lowest probability according to the t-table, which is 0.0005. So our conclusion is that the p-value must be less than 0.0005. And even if we don't know the exact p-value, that is enough to make a decision, because whatever this value is, it will be clearly greater than, less than 10%, 5%, 1%, and even 0.001. Okay, it's less than 0.0005. So whatever the actual value is, it's clearly less than all of these four values of alpha. And therefore, we will have the same decisions, that we will reject the null hypothesis at all the four values of alpha. And therefore, we will have the same conclusion. There's extremely strong evidence to support the claim that the increased competition in the credit card business reduced the interest rates to an average of less than 18.8%. So that's how we perform both critical and p-value methods for a one-sided less than alternative in situations wherein the population standard deviation is unknown. So we have here a summary of what the differences will be for the other types of alternatives. So in this example, we looked at this one, okay? But for other examples where we have one-sided greater than alternative, then the rejection rules will be like this. So the rejection areas will be coming from the right, and the p-value is the area to the right of the test statistic. For two-sided not equal to alternative, we have two critical values and therefore we have two rejection areas. So if the test statistic falls in any of the two rejection areas, then we can reject the null hypothesis. Or using the p-value method, we get the area to the right of the positive uh, critical value, multiply that by 2, and that is the p-value. And if that is less than alpha, then we can reject the null hypothesis. So again, this is the summary for how to perform a t-test for the population mean if this is the appropriate test to be performed.